Okay, over here we have the graph of g of x equals x tangent x on the interval from -3 pi over 2 to 3 pi over 2. And it does look like we have 2 points of concavity, of inflection right here at these points right here. How did I figure that out? Well, I did it on Desmos by taking the first and second derivatives, but I also did it manually by doing this. There's g of x, g prime, use the product rule. First function is x times the derivative of the second is secant squared. Plus the second function times the derivative of the first. Then g double prime equals, I got to use the product rule for that first term. First, x times the derivative of the second, using the power rule. And then the derivative of the side, the derivative of secant is secant tangent. And the derivative of tangent, then the second function secant squared times the derivative of the first, plus the derivative of tangent is secant squared. When I simplified all this, I saw that these two terms combined to 2 secant squared x, and I have a secant squared x in each term. As a matter of fact, a 2 secant x squared in each term. Factored that out, and I'm left with x tangent x plus 1. And I want to know, when does this equal 0? Because that's where I have possible points of inflection. Well, secant squared is never equal to 0. So we have to answer the question, when does x tangent of x plus 1 equal 0? I think I can only do that with a graphing calculator. So if I go to board 2, here's the function y equals x tangent x plus 1. When does that equal 0? At -2.798 and 2.798. So back to board 1, there's your points of inflection at -2.798 and 2.799. Now we would have to confirm that on either side of those points of inflection, concavity changes. Okay, I left that out of the discussion. I'll leave that for you. Hope that helps. There you go.